Okay, thank you. Thank you for inviting me to give a talk about reverberation. So, first of all, I have to apologize in advance. My voice is also down because of a cold, so it looks like the cold season. So, so this talk is going to be about reverberation in AGN, and next we'll talk about black hole binary. So, I'm going to spend a few minutes talking about the general theme of reverberation, and then I will present some of the simulations that I did, or at least some of the estimates that I've done. So, so here we're talking about reflection. So the idea that we are seeing the X-ray comes from the inner regions plus the fast variability. In principle, we are expecting these reverberation signals to be present if these two general features are real. So in AGN, generally we're talking about reverberation in the reflection spectrum. When it comes to black hole binaries, and Ed will talk more about this, there's the reverberation in the black body itself, so that is the thermalization, whatever is the X-ray source illuminating the disks, so that will affect the black body and also the reflection spectrum. Just to borrow from some of the optical studies, when you look at the optical light curves, this is an example of the continuum and H-beta line, and you can clearly see the delays. Of course, in X-ray, things are slightly more complicated because we don't always see the delays as clear as this. Sometimes we do, and the reason is because these are time scale dependent. So if you have two light curves like this, usually on long time scale you see this sort of positive, the red lagging the black, but when you look on faster variability, like in this case, the reverse. And that's why we generally, when we talk about reverberation, we're talking in the frequency domain, and that's some of the plots that we'll be showing. So the Fourier frequency on the x-axis and time lag on the y-axis, and and usually that's the picture that we get. Observation, in terms of what we've observed so far, the first detections came from the soft X's, so this is a standard X-ray reflection spectrum, so that's the black line. The relativistic one is the continuous line, and the dotted is the reflection spectrum without relativistic effect, and the continuum is the red line here. So first we saw it in the soft X's, that is this part here. So if we measure the time delay between these energy bands and the middle energy bands, that's where we first saw the lags. And then we saw it in the iron band, where so this is a study that we did for MGC 4151. When you look at the peak of the iron line, so this is energy, you measure the lag as a function of energy. The peak of the line is delayed with respect to where we think the continuum is, which is somewhere here. So that's what we are talking about when we say iron line reverberation. These measurements seem to sort of fall in the big, when you look at it in the big picture, the numbers are roughly what we expect, so they scale with mass. So this is the soft X's lag, it scales with mass when you look at a lot of the sources. And it seems to be doing the same with the iron line. They also scale with mass, at least to first order, which seem to be what you expect. With the new star, we also saw the lags in the Compton hump. So the first was the soft X's, the iron line, and the Compton hump. And this is why STROBE-X will be really useful, because it covers all of these and will help getting those measurements. Usually, when we present these lag measurements, we present them as a function of energy. So we measure the lag as a function of energy, and that usually gives you the reflection spectrum. So bands that are dominated by reflection would be lagged with respect to bands that are dominated by the continuum. And I just wanted to show this because some of the plots will show lag versus energy, which essentially that will, if our understanding of the spectrum is correct, then you would see the reflection fraction as a function of energy when you measure the lag as a function of energy. Now, how can we, what are the improvements that we're going to get with STROBE-X? The key equations that we're talking about, the sensitivity consideration goes something like this. So this is the uncertainty in the lag measurement as a function of the observables. So here we have N is the number of frequencies that we're, Fourier frequencies that we're measuring, and this is related to essentially how long your observation is and your selected frequency band. And then there are the powers, these are P1 and P2. 1 and 2 refer to the energy bands that we are comparing. P is the power, so this is depends on the object that we're studying, and R is the count rate that we're getting. So this is related somehow to it's sort of the noise factor, and also the background can go into those factors too, and that essentially comes from, you have your given spectrum, what's your detector, and that gives you the rate. So essentially these are the numbers that we have, and then we can get, how good can we do in terms of the uncertainty in the lag measurement. These are phase measurements, but you can convert them to lag measurements. So with simple assumptions, for some of the simulations that I'm going to show, I assume power goes as the black hole mass. This seems to be, at least for some AGN, it seems to be right. I'll show some of the simulations for a typical source of 2 to 10 keV of 4 times 10 to the minus 11 ergs per centimeter squared per second. And then the responses that we have will give us some measure of the count rate that we're getting, and that will give us, how well are we going to be doing. So this is the lag sensitivity plot. So this is energy and the lag uncertainty that we can get in units of Rg. So we remove the black hole mass after the equations. So the plot here is what XMM has been doing. So you see that for the iron unlined energies, we're doing few Rg uncertainties, and that's what the measurement that we're doing, some of the plots that we showed earlier. The red line here is Athena, and then these plots are for XRCA and the lag. The dotted line is for the V-scope parameters that we had, that I had responses for.
Is this in a fixed exposure now?
Yeah, so this is for 100 kilosecond exposure, and what else? Yeah, I assume that's for 4 times 10 to the 11 source, which is sort of, it's not at the right end of AGN, but it gives you some measure. So you see the clear improvement over what XMM can do. Also with respect to Athena, and also it gives you some sense of, at least for the V-scope parameters that we had, so the strongest effect is in the lab, at least for those parameters. When it comes to the XRCA, the difference is not huge, but it's still there, and I'll come back to that point in a second. Here I just show what actual simulations, rather than using the equation to get the estimate. So you always want to make sure that you're getting roughly the right thing. So when I do the actual simulate light curves and add noise and all that stuff, and you get roughly what you ought to get from those estimates. So these are the dust curves here. In terms of flux effect, so these are again the two plots that I had for the 4 times 10 to the minus 11. If you just scale that by factor, so this is going to be for faint sources, slightly fainter sources 10 to the minus 12 ergs per centimeter squared per second, or if you go to the brighter end of AGN. So essentially, this is the range that we'll be exploring with parameters. And as you can see, we're really tapping into the sub 1 Rg time lags, and those are so essentially the measurement will be really at the horizon scale in these sources. Another way of looking at this, and I like to show, this plot is, I like it because it shows really what we've been doing and how well we can do. It's sort of a busy plot, but so what I have here is parameter space where I have mass scale on this axis and the flux on this axis. This is 2 to 10 keV flux and a black hole mass. These are different classes of sources. I have AGN here. Here I just put, ULXs if they are, intermediate mass black holes, so roughly 10 to the 3 or so masses, and also some sources, black hole binaries here with in the soft and in the hard, in different soft and hard state, and also included some neutral stars just to get the idea. And the lines are the 1 RG measurement. So what you see, for example, for uncertainty measurement in the lag, the 1 RG XMM line just about hits, essentially, the way to read this is any source above the line is going to be, detected at least at that level. Lag measurements would be made at least at that level. So XMM is sort of hitting the tip of the iceberg, if you like, and those are the studies that we'll be presenting. Athena will dig deeper, and then when you look at the XRCA and the lag, those are really, you're going to get really into the most of the bright sources. The difference here, the blue are the reverberation map, AGN, the optical reverberation, and these are the just different sources that I collected from the literature. And as you can see, so moving from studying the tip of the iceberg, now you start looking into real samples and studying these plots. Again, the disco plots here, so the lag going from the two parameterization that we had. So again, you notice that the difference in the XRCA, in the lag is larger than the XRCA. So if those two disco parameters are equal in terms of money and mass and all that stuff, then I would go for, I sacrifice the XRCA and leave the lag because that seems to have a stronger effect on those things. Now, what do we do with the measurement once we get it? There are a lot of things, so I'm just going to go through a few things here. One of the things that I think would be really nice to start with is start looking for the signature of reverberation in the power spectra. So the fact that you have a source with some power spectrum, and then that goes into reflection. When you observe the reflection, the effect of the relativistic effect should be also present in the power spectrum, and these should produce these wiggles. I haven't done the actual simulations for STROBE-X, but these some of the early observations that were one of the possible signatures of these things from new start data. So you start seeing these some of these wiggles, and I think these will be easily measured with STROBE-X. Reflection. Also we'll be able to get detailed light energy spectra. So this is what I was showing, talking about earlier. So for example, you look the quality of data that we have now, for example, with XMM. This is simulated, but it looks it gives you an idea of what the quality we're getting now with XMM. So this is lag versus energy, and sort of is meant to be the reflection fraction spectrum. So you sort of barely see the iron line. So it's mostly a change in the slope. This is a plot for Athena. Just I'm putting it here also as comparison. So you see now the reduction in the quality. You start seeing the iron line properly. And again, I'm saying these are for typical AGN flux. So for the brighter end, you'll be doing much better than this. For STROBE-X, you start really seeing the stuff, and even the detail in the continuum, in the reflection hump, the iron line, and also what happens at softer energies. Okay, what do we want to do more? This is what the response function of an accretion disk, relativistic response function of an accretion disk to illumination by a point source. So there's time here and redshift factor, so sort of is the energy axis here. And what you see, this is well known and it's been calculated for a while now, is that the energy, the idea here, what I want to another way of presenting it is when I break it into radii. So what this shows is that the inner radii of the essentially you have a flash and you illuminate the accretion disk, and then you measure. You see the delays coming from different regions of the disk. some of the early response comes from the inner regions. These are the highly redshifted part here because they're close to the black hole. And then as time progresses, you see emission from the outer regions. So the inner disks response from the inner disk will be somewhere here, and then the response from the outer disk will be from here. Just showing here again. But what you notice also, the changes, the fast variability will come from the inner regions, while the long-term variability will come from the outer regions, and this will give us an idea how we want to observe these things. So essentially, if we look at light energy plots at different time scales, this is what you expect. This is again simulations for 100 kilosecond, and you start resolving these features in the iron line and the Compton hump and the lag. So the green line here is the early response coming from the inner regions, where you see is redshifted, and then as time goes by, you're seeing the blue peak, the blue wing of the iron line. And I think what is interesting here is that not just we'll be doing this with the iron line, but also given the XRCA response, you start seeing these features also in the soft energy. So if at least part of the soft axis is due to reflections, and then some of these features are also important. With these measurements, you can go and try to build back so you measure. What we measure is the energy on the axis, the response as a function of energy and frequency, and then you can go back and try to reconstruct this, and that hopefully gives you an idea of what the geometry of these systems are. I think there was something that I wanted to talk about. Yes, there was the energy resolution here. So these plots are I used the. It doesn't matter which one I use, because my energy resolution in the simulation was much higher than that. It was about 800 eV. So I haven't explored, how far you can do with the energy resolution. So as far as these simulations are concerned, the two, what we had, the 200 or 300 eV is the same. I think at some point there is a limit how far you can go, because if you make your energy, as far as the lags are concerned, if you make the energy resolution low enough, then you won't have enough signal in the energy resolution. I don't know what that limit is, but I think we can work that out. So I think the interesting part here is that the quality of the lag energy spectra will be comparable to what we are getting now with XMM. Well, not what we're getting with XMM, but at least we'll have some good quality that we can really start to fit properly these models. And there are different ways of doing this. People have been exploring how we can measure, try to fit the whole frequency and energy axis at the same time. So my summary slide here. So again, some of those plots that I showed really show that we are now just looking at the tip of the iceberg. With STROBE-X, you really get even start getting looking to larger sample, trying to having larger sample will give you the bigger picture of what's going on. Something that I haven't talked about are the orbital gaps, of course. I think we understand these things, at least with the experience with Suzaku and U-Star. So it's not really. We can do the measurement even with the presence of optical gaps. Of course, because these are periodic gaps, then we're going to miss some of the interesting time scales, 10 to the minus 4 hertz or so, 10 to the minus 3 hertz in some AGN. But the positive side, the positive thing is you get also the long time scale, because with XMM you get the continuous coverage, but the maximum observation you get is 100 kilosecond. Usually, if you want. Usually, you can get 2 observations, but that doesn't work. With the U-Star, for example, we can, although we miss some of those short time scales, we can get really long observation of weeks time scale to probe the long time scales. So STROBE-X will be probing sub RG lag, providing sub RG lag measurement, which is really opens really some new frontiers at the horizon scale. And one of the key hope, the measurement that we would be able to do is measure the relativistic response function, so we can really probe what's going on at those scales in terms of geometry and and what's going on. And this is just the last point I put it here. In terms of, at least for the D-scope parameters that we had, I would, the XRCA seems to be less sensitive as far as these lag measurements are concerned compared to the lab. And I will stop here. Okay.